and then I'm going to broadcast, and we are live. Hello, everybody. Welcome. Thank you for joining us. We'll slowly be getting more and more people coming in. So if you haven't joined before, or even if you have, please put in the chat your name and where you're joining from. We'd love to see that. Already fairly spread out. Maryland, Arizona, Peru, Oregon, Cape Cod. Looks like someone is from Hawaii, Aloha Bo. Argentina, Missouri, Tennessee, Kolkata. Wow, that's late there. Mexico, Colorado, England, South Africa, Wiltshire, which I assume is in England, but could really be anywhere.
Philippines.
Ooh.
Hi, Gladys.
Belgium.
Germany.
Hey, Connecticut is just fine.
Connecticut. Hi, John.
Greece. Oh, some more from the Philippines and Venezuela. That's a new one. England. Another person from Greece.
It's quite a long way down the road.
Diverse crowd, just like normal. And Italy. Ooh. I'm always impressed by how many people will join very late at night. I have not seen anyone from Australia or New Zealand today, but I have in the past, and that's dedication, man.
Hey, we're astronomers.
True, but I don't know, 6 o'clock in the morning just isn't a good time, no matter whether you're waking up or still up. It's just, hey, Arkansas. Northern Arkansas. I actually am from Northern Arkansas. Originally West Memphis, and then I moved to the other side of the state to Bella Vista or Bentonville. Actually saw someone from Bella Vista at the last one of these, but let me connect this. Sorry, while this is up, I can't see anything else. So, we'll wait just one more second. Thank you all for coming. I'm gonna start introducing everything in just a second. This has been a wild ride for me and for the observing sections in general. As you can tell, we're about 3/4 of the way through everything. And we've had an amazing turnout to these so far. People seem to be very interested in them, and we're extremely glad that they are. Today in particular, we're going to talk about young stellar objects. Our panel today is Michael Poxon, Bo Rayperth. I should have asked you how to say that. I never did. My apologies. And
Right.
William Hurst. This is actually a treat for me because young stellar objects are probably the thing that I know the least about from an astronomical standpoint, at least as far as variable stars go. There are plenty of cosmology things that I don't know anything about. So, but from a variable star standpoint, this is the thing that I know the least about, unless you count massive stars. But since they're all technically young, I feel like that doesn't really count in this sort of designation. Before we start, I'd really like to thank our sponsors. They make this much easier for us to do. As those of you familiar with Zoom webinar might be, it is not exactly the cheapest service in the world. So having some sponsors allows us to be able to do this and allows us to have many more participants than we would otherwise be able to have. In particular, I'd like to thank Voice Astro. The Voice Astro provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools to learn how to perform observations, conduct research, and publish their results in scientific journals, like the AAVSO. And they have been a close ally to the AAVSO for years. So thank you very much. I'd also like to thank ATIC Cameras. They manufacture a diverse range of quality astrophotography cameras and accessories, along with a range of free software to help you maximize the output of your equipment. For more information, please visit their webpage. As always, links for our sponsors will be found in your post-webinar survey, as will any pertinent links that happen in during the course of these talks. I'll make a record of them and make sure that they're in that email as well. So without further ado, I'm going to introduce Mike Poxon to start us off.
Okay, Bert, thanks for that introduction. I hope you can all hear me because we did have a few problems with sound earlier, but I'm assured it's okay now. So if you can all hear me, just kind of jump up and down or something. Okay, right. I just want to kick off really by saying how flattered I am to have can I call them assistants today? Because these two guys are they are absolute first magnitude stars in the field of YSO studies. So it's great to have them here too. Are you getting me, by the way? Are you hearing me?
Yes, we are. Oh, and one other thing. Sorry, I forgot to mention this. Sorry to cut you off, Mike. But I just wanted to tell you, if you have any questions, and I know that you probably will during the talk, there is a Q&A button. Please ask all your questions there. I'll try to see them if they're in the chat, but it's much easier for me to find if they're in the Q&A. So please try to address any questions there, and we'll get to them in the Q&A session at the end.
Okay, I really want to kick off with just a kind of an overview of what YSOs are and the kind of YSO zoo, if you want to call it that. So this is going to be in the form of a series of web pages, because I used to be a web designer, so that's fairly sort of, it's a fairly logical thing to do. So if I share my screen now, are you seeing that? Are you seeing the strange cloud in the middle? I assume you
Yes.
are. Okay. Right. So we'll kind of we'll sort of kick off. Sorry, I'm just trying to do a bit. There we go. Right. This really is where the story starts. All stars are formed, or as far as we think, all stars are ultimately formed in giant molecular clouds. These are very, very cold places. They're about 10 degrees above absolute zero. But even so, that's still warmer than the areas that aren't giant molecular cloud. So compared with the background of the interstellar medium, they are warm. I mean, we can't actually call them hot, can we? But they are comparatively warm. But they are at such a temperature that we get the formation of molecular hydrogen, not just the pure hydrogen. In terms of mass, and when we say mass, really what we mean is how much stuff there is. All right, that's a really easy way to understand what mass is. Mass is stuff. So how much stuff is there in one of these giant molecular clouds? Well, this one here, which is in the southern constellation of Orionis, the actual numbers vary, but probably at least 50,000 times the mass of the Sun. Now, obviously, this is a very, very large area, and the dust is fairly thinly spread, but there's an awful lot of it, which is why it blacks out anything that's on the other side. The other thing to bear in mind is nothing in the universe is still. And certainly the galaxy isn't still, it's rotating, obviously, and carrying the stars and the clouds of gas and dust with it. So stuff is always churning around, and sometimes this churning can cause the black bits here, just the molecular hydrogen, and general space gunk, if you want to call it that. It can start off a process whereby this gunk, this gas and dust, etc., can actually start to condense, and that is the start of the star formation process. This is a picture of, this isn't a giant molecular cloud, but it's still a big molecular cloud. It's in the constellation of Cepheus. It's a particular, very, very interesting part of Cepheus called the Cepheus flare. If you think of the constellation of Cepheus, winds drawn between stars, as a sort of a steep roofed house, and basically the Cepheus flare is the loft. It's the bit underneath the roof. Okay, it's quite close in terms of star formation areas. This one's about 150 parsecs. That's about 500 light years away. Now, as you can see on here, there are distinct areas in this cloud, and in fact, we have found, if I could just click on the picture, these are all areas where we have found infrared sources. Obviously, the stars haven't formed yet; they're not bright enough to shine visually, but they are giving off more heat, which is where the infrared comes in. So we can see the heat, even though we can't see the stars. There's all sorts of stuff going on here. There's not just these few sort of areas of forming stars. There's all sorts of other dynamic things happening. But this is where our stars form from. In terms of astrophysics, mass is always very, very important. And for the purposes of this talk, we need to know that stars that are about 2.5, 3 times the mass of the Sun will end up, in terms of variable stars, as what we call T-Tauri stars. More massive stars, simply because they are more massive, will behave differently. But they're all variable, so that's where we're interested. Okay, this is the basic way that a star is formed. Those clumps that we saw earlier, our forming star will be formed out of these clumps, which, as the motion of the cloud tends to move them around, they will tend to congregate and they will become slightly denser. Eventually, they will become so dense that we have our forming star in the middle, a little centre of gravitational attraction, if you like. Now, this is a process of what's called positive feedback, because gravity depends on mass. Then, as our forming of protostar, if you like, starts to accrete more mass from the surrounding cloud, which is being compressed by various sorts of motion. Obviously, the more mass it gets, the more gravity it will get. The more gravity it will get, the more it will suck stuff in, and it builds up. It's positive feedback. Now, obviously, in the universe, everything takes time because everything is much, much bigger. The general time scale for the actual sort of cause collapse is measured in thousands of years. So in terms of human lifetime, yes, it takes an awfully long while. In terms of things that happen out in the universe, it takes virtually no time at all. This is why we see things happening with a fair degree of rapidity, because everything here is is speeded up from what we are used to. We're used to stars living for billions and billions of years, or we're now talking thousands of years. Things are speeding up now, and other stuff, other mass will tend to fall in, making our star warmer and denser and more massive. At this stage, we will kind of reach a point where the excess material, because this stuff is constantly being kind of sucked into the star, the excess material will be expelled through the points of least resistance. Well, obviously it can't go out this way because that's where everything is coming in. It's like trying to get out the door, kind of when you've got a howling gale blowing against you, blows the door against you. So the points of least resistance are the poles, and this is how we get what are called bipolar outflows. The infall of material here can actually affect the way that our baby star varies. So sometimes we can get times when there is massive infall, real sort of major times of download of this material onto the star, and the star will appear to brighten by really a fair old amount. These major kind of episodes give rise to what are called FU Orionis stars. Now we don't see a lot of this, simply because these major infall episodes are very rare. But one was observed, I think it might have been in the 1930s, on a previously faint star called FU Orionis, and I think it rose from about magnitude 15 or something up to about 9. The same thing happened to a star that I'm a lot more familiar with, which is V1057 Cygni, which is right in the North American Nebula. That rose from magnitude 16 in the 1970s up to about magnitude 10. Basically what these stars do is they rise up to this magnitude and then they stay there for an awfully long time, because all of this material has been dumped on the star, so the star becomes brighter. But these are fairly rare. They are rare occurrences, which is why we don't know of many FU Orionis stars. They're not so much FU Orionis stars, but the FU Orionis phenomenon is, it's a stage in the formation of a star. It's not necessarily a different type of variable star. It's just an episode in the life of a young stellar object. This happens to T Tauri stars. I'm not quite sure whether the same thing happens to the higher mass stars, which we'll come to a bit later. T Tauri stars are eventually going to end up as stars like the Sun. They're not enormous, they're not overmassive, reasonably late spectral types of GK and so on, that kind of thing. So sometimes when we get our outflow from the star, this is a very interesting it's a very interesting part of its history. You can get what are called Herbig-Haro objects, or just called HH objects. Now here is some. This is an actual HH object. Now, as you can see, presumably the star is in the middle here somewhere, and this expelled gas is creating oceans in the surrounding gas, because don't forget, this is all in a highly gaseous area, and these can actually set off other bursts of star formation. But if we just kind of go back to our picture we were just looking at, our little schematic, okay, the dark bit here is the equator. Obviously the star hasn't formed yet, so we can't actually see the star. That's why it's dark. it's probably radiating in the infrared here. But here we can see the gas being expelled from the cones, which, as you can see, both these pictures are at right angles to the equator. So that's kind of that. What I really want to look at now are actual stars, and sort of see how all these various things, all these various things that are happening in this highly dynamic environment can actually give us our variable stars, which is what we're interested in. Okay, so I actually want to look at T Tauri itself to start with. This is from a paper by some astronomers in the Ukraine, which is that's a huge centre for YSO studies. They're really mad on them there. T Tauri, as a rule, because we think one of the main reasons why it varies is because they are fast rotating stars, and so they have star spots, which can make the star appear to vary. Now, as you can see here, it's not varying very much. It's only varying by about sort of half a magnitude, and it's reasonably regular. So it's kind of almost a sinusoidal-like curve. Nothing terribly sort of drastic going on, except here. The astronomers who produced the paper that this is taken from saw an event. All right. I'll start that down here at magnitude 10, and it jumps up here overnight to about magnitude 9.3. So something strange may have been going on there. Now, where us variable star observers come in, wouldn't it be brilliant if someone from, say, the AAVSO happened to be watching T Tauri at this time? They would have been able to confirm it, because the astronomers who did this actually themselves said that it's an unconfirmed observation. Wouldn't it be good if someone could actually confirm that? But I don't think anyone was watching T Tauri at the time, which is a bit of a shame. We'll see later that other stars act equally quickly and surprisingly. Now, another T Tauri star that I like to look at is FU Orionis. Again, normally it tends to vary like this, and actually roughly about the same magnitude as well. Kind of sort of variable, but not. It's not SS Cygni. It's not violently variable. It's nice and gentle as the star rotates quickly, complete star spots, other things that are going on. But on this particular occasion, we could see a huge dip happened. This happened literally 2 days before I was due to give a talk at the joint AAVSO-BAA meeting on a completely different star. 2 days before, I had an email from Bart Stales in Belgium, who said, "I think you should have a look at FU Tauri." And yes, it's undergoing a huge dip. This, I think, is from the same paper that this one is. Basically, the wavelength is higher at the top. So this is infrared. So as you can see here, not a lot of variation is happening, because probably what's going on here is this is largely the combined radiation from the star and the gas cloud that's surrounding it, or possibly even the accretion disk. So not really very much has changed there, but whatever has gone on is probably veiling the star, so it fades in the shorter wavelengths. I think that's what's going on. I stand to be corrected. Now we can go on to another star in the same constellation. In fact, before I get there, FU Orionis is a really interesting star observation to look at, because it's a double star, quite a wide double star, and its companion, which is actually brighter, is also a YSO. Its companion is AB Orionis, which is more massive and behaves slightly differently. But you can actually physically observe these two stars at the same time, because they're quite close to each other in the sky. Not far away, we've got RW Orionis, which has been known for ages and ages as a variable star. And again, this is a normal pattern of behaviour, just the way it behaves as a rule, varying between about magnitude 10 and about sort of 11 and a half. well, look at this. Whoa, what's going on here and what's going on here? Well, if we just have a look at this, I'm not quite sure what sort of wavelength this is in. I'm sure someone will tell me. But this actually reveals the presence of bodies of gas and all sorts of things, and it's all these bodies of gas are moving around. RW Aurigui is a double star, and possibly what's happening here is its companion is interacting with RW Aurigui itself, the main star, and it's pulling some of its gas off. So you know, this is all very interesting dynamic stuff that's going on. So there again, this is a really good reason for amateurs to follow these stars. This was a really interesting time. I mean, I actually thought it was never going to get. I thought it was never going to get bright again, but it did, and I think it's back up to, you know, to where it sort of normally is. But obviously, it has to be looked at on every clear night because we simply don't know when these episodes are going to happen. So all sorts of interesting stuff happening here. These are fairly low mass stars, not too unlike the Sun was about 5 billion years ago. So let's have a look at the higher mass stars, which are kind of quite a lot more active. These are stars that are between about 3 and 8 times more massive than the Sun. Obviously, they're more massive. Everything works differently. They evolve quicker. When I first started observing this star, which is V730 Cephei, it didn't actually have a variable star name. It was a very new discovery, and it was found to spend most of its time near maximum of about 13th magnitude. But at one stage here near JD517, it plummeted down to magnitude 16. Now, I happen to know that this particular observation there is mine, because that's the faintest the star has ever been observed at 15.7. And later in the same day, I heard from, I think it was Mike Simonson over in the States there. He had a look at the star. This is the same day, and he made it magnitude 14.2. So it had risen by a magnitude and a half in less than a day. It's a very, very active star. Now, at this stage here, it's quite irregular. But if we look at the second half, we can see these periods here. We've got a dip there, we've got a dip there, we've got a dip there, and the period of these dips is about 13 days. From actually analysing the star and sort of looking at it in various wavelengths, we think what is probably happening here is we have the formation of either a planet or a planetary system, and the plane of the orbit is kind of, you know, it's kind of onto us. So we are looking at the equator of the star and the accretion disk surrounding it, out of which the planetesimals are in the process of actually accreting into the accretion disk. And it looks as though one of these planets is presumably really fairly close into the star, because the period here is about 13 days. It could be one of those hot Jupiters, who knows. The clump that will become this planet is orbiting in about 13 days, and every time it passes between us and the star, it causes a star to fade. So these stars, we call them Haeves, H-A-E-V-E, because they're types A and B, and they show hydrogen emission. That's just why they're called Haeves. Again, I stand to be corrected here, but I generally find that these early spectrum type stars, the Haeves stars, tend to be single stars, whereas the T Tauri stars are more often double, or in the case of T Tauri itself, triple. Possibly why these stars show much more activity is, as they're more massive, there's actually stuff there to cause these episodes. I've called it causing trouble. obviously for variable star observers, it's quite the opposite of trouble. It's great stuff. So here we have another star. This is RR Tauri. That extremely active. If you just look at the grid here, all right, these spaces are 20 days, so really fast variation going on. I think RR Tauri also emits X-rays, so it's obviously a very active, very dynamic place. Another interesting star, very close to RR Tauri in the sky, and I think also in space as well, is a brighter object, in fact, always visible in small telescopes, so please observe it, which is called CQ Tauri. Now, sometime in the 90s, I think it might have been in the 90s, might be a bit later, I was observing CQ Tauri, and I saw it plummet by almost the entire magnitude in the space of 20 seconds. Now, I'm presuming this is unconfirmed, as was the case with the spike of T Tauri by the Russian astronomers earlier. I'm just assuming that nobody else saw that. I'm also obviously assuming that it was real. You know, none of the other stars in the field faded apart from this one, so I can only conclude that it possibly was real. This sort of thing, obviously not from the same kind of cause. The same thing has been seen in some cataclysmic variables flickering over the course of seconds. So obviously something is going on here. I just want to take this on a bit and look at an actual star, one star. And this is a star that I'm very keen on, V1117 Hercules. It's so interesting. Something I think that a lot of our members could do is to use VSX a lot more. It's really good. For instance, I've pulled some figures for this star out of VSX. Now, obviously, forming star is going to be attended by an accretion disk, swirling gas, and all this sort of stuff, which radiates very strongly in the infrared. So what we're looking for is an infrared excess over other sorts of radiation. So what we're doing is comparing this, which is the infrared, that's J minus K, with what used to be called the colour index, basically how red the star is, really. And that's our B minus V. Now, this star is of spectral type A, so the colour index is going to be quite small, as you can see it is, almost half a magnitude. But the infrared excess is 2 whole magnitudes, and that's what we want to look for, where the infrared excess here is bigger than the B minus V here. Okay, so that's a good clue to here we have a YSO. Okay. What makes this star really interesting is that it's not in an area of star formation. In fact, it's 33 degrees above the plane of the galaxy, so a long way away from any gas clouds or anything like that. But the really fascinating bit about it is not only is it not near any gas clouds, but it's actually coming from even further outside the plane of the galaxy. And as you can see, what we have here is a bit like what we have in the case of V730 CPI. We have these semi-periodic dips. One probably happened there, but we don't have the evidence. And another one here, and another one here. Now, in the case of this star, these events are happening about 400 days apart. So if again, we do have a forming planet here, the interesting thing about it is, if this star is massive, and it's of spectral type A, if this star takes if this forming planet, for instance, takes roughly about 400 days to go around its parent star, that would put it in V1117 Hercules' Goldilocks zone, where it eventually becomes a planet. So I think that's brilliant. Right, so we've kind of looked at very young stars. So let's see what happens start to age. All right, so we're kind of looking at baby stars really. So what we want to look at the sort of those sort of toddlers and children in terms of stars. They're growing up. Okay, now just got a little graph here. As you can see, there are no numbers because it's simply to show a tendency. As stars approach the main sequence, obviously the sort of very definition of a YSO is a star that hasn't quite reached the main sequence yet. It hasn't started to fuse hydrogen in its core like a proper star would. So this is why they're called young stellar objects. Right? They're not strictly stars yet. And as our variable star approaches the main sequence, its variations become less, and that seems reasonable. Of course, most of the things that are causing the variations, the infalling gas and dust, the star spotting, that's all calmed down a bit, because a large amount of the gas and dust is either starting to form into planet, it's been blown away through the bipolar outflow, and so on. So there isn't quite so much gas and dust to cause trouble, if I could use that phrase again. And when our star eventually does enter the main sequence, which we've got here, stars of various mass, it actually enters at a slightly brighter stage to where it will eventually kind of subside and become a normal, non-variable, boring run-of-the-mill star like a star. And that's because it's still a little bit bigger than it will eventually calm down to, because it's still got some of that stuff left over from when it was forming. So the star is a bit bigger. It's got a larger radiating area, so so it's a little bit more sort of luminous. Okay, and at this stage, you might find around our star a debris disk, partly probably as a result of the planet formation process, which we'll have a look at in a minute. But it's worth bearing in mind that even after 4 billion years and the rest of it, our sun still has some of this stuff left over. That's what the zodiacal light is. It's sunlight reflecting off its old debris disk, or what's left of it. So if you ever seen the zodiacal light, that's what it is. Right, I just want to look at the youngish star now. All right, so our star is now it's a sort of a teenager. It's just gone through puberty. Beta Pictoris, which a lot of people may be familiar with through this picture, which has been lots of times, and this is actually a view of, okay, it's not a YSO, but it's still a very young star, and it's still got its attendant disk. And we also know for a fact that there are planets now orbiting Beta Pictoris. There are planets in the sense of virtually formed planets, but there are also planets still actually forming. So, all right, even though this is now a bona fide star, it's still, if you like, carried some of its youth and its the things that characterize its youth. It's carried them with it. So even though it's not technically a YSO variable star, it's still a very interesting place. It's a star a bit like the sun. It's a bit bigger. It's a little bit more sort of massive. It's a bit more luminous, but it's essentially it's a sun-type star. And as you can see down here, various depictions of planets and so on. I will put these pages online, so if you want to sort of follow the whole thing. Of course, one great advantage of studying YSOs is that you get to see lots of pretty nebulae, because that's where they form. So I just want to show a few pictures, not pictures for picture's sake, right? So there is a reason for these. So picture time. Okay, these pictures are taken. This is quite interesting. By a childhood friend of mine. We actually used to play together as kids in the same street. He wasn't interested in astronomy at the time. His family emigrated to Australia, and several years later they came back. And I was browsing our local astronomical society's website in Norwich, and I found his name, Sean Reynolds. And I wonder if that's the same one as the kid I used to play with, and yes, it was. He is now interested in astronomy, and he is one of Britain's leading, I think they call them astro imagers. He's absolutely mad keen on his images. His images have been used lots and lots of times. There's a link to his website. Very, very small commercial break. Right. This, as a lot of people might recognise, is the Elephant Trunk Nebula, again in Cepheus. Cepheus is brilliant for ISOs. IC 1396, and I think technically it's IC 1396A, but I'm not going to bother with the A. And this is an area of very, very intense star formation, all kicked off by this. This is a 5.5 magnitude star. It's actually triple. I call it the Northern Trapezium. It's actually the centre of a newly formed open cluster called Trumbull 37. It's extremely powerful. It's extremely hot. It's of spectrum type O, so it puts out a lot of very intense radiation, which is basically responsible for most of this. So I'll just click on the picture, you can see what we have here. Okay, there's our star, Trumbull 37. Here we have GM Cepheid, which is one of these higher mass YSOs. Varies from about magnitude 13 down to 16, so you need a decent telescope to see it, but it's worth watching because, again, it's one of these highly irregular objects, and we think it's also called the planetary system as well. The other really interesting part of this is this area here. Now, visually, you can't really see very much there. Yes, there is a B390 Cepheid there, which is of course a YSO. But if we look in wavelengths other than visual light, we can see that there are actually 30 or 40 forming stars simply in one dark area. So very, very, very interesting things going on in this nebula. So it's not just a pretty picture. We're nearly there. Right, this is a propeller nebula. This is in a star-forming area in Cygnus. Now, the thing about this is, I'm not sure if it's a YSO. I tend to think it is, because if you can recall back to our pictures with the equator of the star and the bipolar outflow, here we have a dark band there, which kind of looks to me a bit like the star's equator, of our forming star. And here we have a bipolar outflow, which is, yes, it's symmetrical, but as you can see, it's not straight, hence the name propeller nebula. So I think what could be going on here is we have our forming star here, but there might well be something on the other side of it that we can't see because it's being obscured by all this stuff that may be influencing the path of the bipolar outflow and bending it like this. So that's that's just my idea of what might be happening. I don't know if it's actually true. Okay, so here's a picture. Now, something really, really interesting is literally last night I had an email from AAVSO HQ saying that someone had seen an erupting star in this nebula. This is literally overnight. So we have a star appearing where one wasn't before, and this is a very, very intense area of star formation. There's all sorts of stuff here, not just young variable stars, but there are those big Harrow objects we looked earlier, the outflows, lots of infrared sources, which was protostars. So it's a very, very intense area of stuff going on. And we've got a nice open cluster in the same field as well. There we have the V373 Cepheid, which is one of these sort of dipping stars. I've observed it dipping. We have the V361 Cepheid, which is a star more or less of the same sort. It's not quite as active, not quite as interesting from a sort of visual amateur point of view, because you do need to bear in mind that, speaking personally, I only observe visually, so that tends to be what I'm interested in from the observation point of view. And we have another YSO here. So again, this you know, this kind of got me rather interested because I'm thinking, it's a big talk tomorrow, isn't it? And we've got a brand new star appearing in one of the pictures that I'm going to show. Well, it turns out, I think, that he hadn't observed a new star. I think what he possibly observed was this, which is a little knot of these Herbig Haro objects. So I think that's possibly what he saw. So, you know, I was very, very excited at that time. It's quite late in the night. But obviously, you know, I wanted to, sorry about the pun, but I just wanted to put that to bed first. So it's not a brand new sort of Vulcan YS, unfortunately, but it's still an interesting observation. Okay, so I think that's all you're getting from me, and you'll have to listen to someone else. So I'll stop screen sharing now.
I know Bo is going to speak next, and I just wanted to say, Mike, thank you for a very nice description of an overview of the variability. But just before Bo speaks, I wanted to make one tiny little addendum or correction to what you said. I think you have to make a distinction between primary disks, which you were talking about, and that beautiful picture of how T-Tauri stars form and all that stuff, and secondary disks, debris disks, as they're called, like Beta Pictoris and like the zodiacal light in the sun. So the zodiacal light from the sun is not a leftover from the primary disk of our nebula. That disappeared. That was 4.5 billion years ago, and that stuff is all gone. The primary disks go away probably in about 1 million years or so. But then these secondary disks, like the zodiacal light and like the Beta Pictoris, get generated by all kinds of processes that occur in the disk, like collisions between asteroids and stuff like that, and comets throwing off stuff, and so that stuff actually gets swept out of our solar system on a time scale of just a few million years. So the zodiacal light isn't really a remnant of the primary disk. It's something that's generated all the time and continues to be generated, and continues because as the stars go around, as dust goes around, it suffers what's called a Poynting-Robertson effect, and it has friction with stellar photons, and it spirals in. So it gets formed out there by collisions in the asteroid belt and comets and stuff, and that stuff just is on a conveyor belt and swept out of the solar system. So they're actually two separate phenomena, and quite beautiful. But thank you for a really nice overview. And now I think Bo is going to go next.
Well, I will start out just asking you, Mike, the very first slide that you showed showed what looks to me like the Vandenberg-Herbst 65A nebula, which our own Bill here discovered way back, what, 40 years ago, more?
Or more, or something.
So, Michael, what image was that? It looked like it was HST resolution.
Apparently, that's the Circinus giant molecular cloud.
Right. This little object is located in these clouds, so I just had not seen that image before, and I'm interested in it because I'm working on a big paper precisely on star formation in that large star forming complex, which has been very poorly studied. And I was unaware that the Hubble Space Telescope had taken such an image. So if you could let me know where you found that image, that would interest me.
Yeah, I'll try and find out. Yeah.
Okay, great. And the other question I have is, you say that your friend Sean had seen this possible eruption in ATC 7129, and that there is an HH object where he found something. But if he says there was an eruption, it must be because he's looked at an earlier image where it was not seen. Since the HH object is not something that is going to pop up, something must have changed. Do you know if why he said that there was a change there?
I don't myself, but the person you really need to contact is Elizabeth at AAVSO, and I think Sebastian Otero was involved with it as well. And in fact, I think it was the Assassin, ASASSN, the Assassin survey actually looked at the area very soon previously and found nothing. But if you contact Elizabeth, she will fill you in on all the toing and froing of emails between various people.
Okay. Well, if Assassin has not seen anything, then there was no eruption. Assassin is
exactly.
Sophisticated endeavor. Okay, let me share my screen here. Hang on. Let me share screen and do you see? What do you see? Hello?
We don't see anything right now.
Okay, I try to press share screen. Okay, and share. Do you see my screen now?
Yep.
Good.
All right. Okay. Let me tell you a little bit about the FU Orionis eruptions. These are objects that have fascinated me for my entire professional life. And they are important objects because they tell us about some very special episodes of the early stellar evolution. And the whole thing started, of course, when in the 30s, 40s, that the Tauri stars, they were recognized. And all of these stars, they are, just as Michael has described, variable because they have interactions with their disks. Whether it is because material is dumped onto the star to make it brighten, or material in the disk is obscuring the star, as Bill will be talking about. The disk is the key to all the variability, and the disk interaction with the star goes through, is due to the connection, magnetic field connections, which can be very complex and that theoreticians still don't completely agree on. But for the FU Orionis stars, the story started back in 1936 when a small anonymous variable star of 16th magnitude, FU Orionis, erupted within less than a year by 6 magnitude. And this is in the Lambda Orionis cloud, the head of Orion. It's one of the clouds there that's called Barnard 35. And this has been, for many years, this was considered just an abnormality and of no real interest. But then George Herbig discovered several more of these objects. And here you see a mix of light curves set on the same time scale. So you can see that they have certain things in common, namely brightening, but the brightening does not always happen over a short period of time. In fact, we have one that took 15 years to brighten. But what they have in common is that they stay bright for a very long time. We have some objects that I will talk more about at the very end that have shorter, they're staying at the high state for shorter periods, but I'll get to that at the end. Now, why would a star erupt like that? And the reason is that material has been dumped on the star, and there's some kind of enormous energy release because of the gravitational energy that is added to the star. But why would a a disk that normally is quite well behaved suddenly start dumping stuff onto the star. And there are many different ideas about what can trigger these events. My favorite idea is that this is because a binary companion is plowing into the disk of the star that erupts. And this can happen because when stars are born, they're very often born in small multiple systems. Triple and quadruple systems are actually a normal big starting stage for young stars. And then they will move chaotically among each other. And this can lead to ejections and in some cases outright escapes from the system. And that's how we are likely to form a lot of the single stars that we see in the Milky Way. Anyway, if you're left with a triple system, one object is ejected, the energy that is required to eject that star will bind the remaining two stars together in a tighter orbit. And so this will be a highly eccentric orbit. And when the companion then gets close to periastron, it will be able to plow through the circumstellar disk. And that means the disks are not these nice disks that you see on ALMA images of HL tau. They can be very distorted. And these kind of large tails can be responsible for these major dimmings that Michael was talking about in RW Auriga, although I should say RW Auriga is not at the moment an FU Orionis system. Okay, so let me tell you a little bit about some of the objects that have been studied. One of the most exciting discoveries in recent years started out with an amateur, Jay McNeil, who is located in Paducah, Kentucky. And he rolled out his 3-inch refractor into his driveway and took an image of the Orion B clouds. And he saw something that he was puzzled about. So he went to the Sky Atlas and checked, and there was nothing there except a little Herbicera object. But the Herbicera object was much, much fainter than this nebula. So what he did is he contacted various people and they directed him to me. And so I got this email one morning. I got to work. Dear Dr. Reipurt, I have found this little smudge on my photo. And I said, oh my God, I don't have time for this kind of stuff. But I nonetheless went and looked at the region, and lo and behold, he had really discovered a new object, which is extremely rare. So here's what you see on the Sky Atlas, which he had been studying. And here he then built a 10-inch reflector and took this beautiful image where you can see in the lower right the nebula that is now named after him, McNeil's Nebula. So I immediately requested director's discretionary time on the Gemini 8-meter telescope. And here you see what this object looks like. What you see here is a star that has erupted from being essentially invisible before and illuminating a pre-existing cavity. And this cavity would have formed by one of these the bipolar outflows or winds that Michael has been talking about. So that was really exciting. And Jay McNeil, let me just go back here for a second. Jay McNeil became very famous for this. I remember one morning, one Sunday morning, I opened for BBC News, and there was Jay McNeil explaining how he had been discovering this. And this was particularly interesting because this kind of monitoring was something that was not possible to do by astronomers, because astronomers can get only a little bit of time on big telescopes and they have to devote it to very specific projects. Now, I will mention to you at the end here, we are in a better position to know what's going on in the sky. See, the FU Orionis objects, they have in the optical spectral types of F or G. But then if you go to the near infrared, then you see that they have spectra as if they were late M stars. And this has been seen only in FU Orionis objects. And it was for many years a mystery until it was realized that what we are seeing in FUs are no longer the central stars. It is the surrounding disks that have become very, very luminous, as much as 100 times brighter than the star. So it completely drowns out the light of the star. And therefore, when you look in the optical, you see the innermost part of the disk, which is hot. And so it will have an F or G type spectrum. Whereas at near infrared and mid infrared wavelengths, you're seeing the very outer parts of the disk, which are much cooler, and therefore you have a later spectrum. So you can see this here is a series that my colleague Mike Connolly and I have been taking with the NASA Infrared Telescope facility at Mauna Kea. And you can see that all of these objects, these FU Orionis objects, and they represent all the known ones. So you can see we don't know a lot, it's like a dozen. They have very, very similar spectra apart from different extinction. So one question that, of course, came up is, when did this eruption start? And so there was a campaign among amateurs to look through their observations, and it was determined that the nebula actually started to appear in the fall of 2003. And when that was known, Venezuelan astronomer Cesar Briceño, he went and looked at a series of images that they had just been taken to study variability in that region at the same time. And lo and behold, as you can see in this sequence of images that goes from the 24th of October 2003 to the 26th of January 04, you can see how he was able, by sheer luck, to catch the eruption as it occurred. Okay, so then the question is this a one-off or has this happened before? And so again, amateurs looked through lots of images and found one image taken by an amateur, Kramer, back in 1966, where it was visible. And so we contacted the Asiago Observatory in Italy, which has done a lot of photographic monitoring of star-forming regions since the 1930s. And they were able to recognize and confirm what Kramer he had found. Now, in order to find such objects, I decided to make a project where that was dedicated to monitor star-forming regions. And together with my colleague, Josh Wallerwender, who is a staff astronomer at the Keck Observatories, we have developed a little observatory which is up at the Mauna Loa volcano. And it monitors, two small telescope monitors star forming, about 100 star forming regions every night. And if you want to know more about this, there is a link here below where you can see more about the goals. And these are quick exposures, 2-minute unguided, and we're just looking to see if something has changed. And unfortunately, we were having an intense campaign on the North American nebula. But at one point, we were down for half a year. And of course, right during that time, there was an FU Orionis eruption occurring in that very region. So we missed that. Fortunately, other surveys caught it. And as you can see to the right, there's a dramatic rise in the light. Another amateur, Jim Toms from San Diego in California, he took the image to the right and saw this nebula in the middle that was not seen on an earlier of his images. And he contacted me, and I got some observation and confirmed that this is a bona fide FU Orionis object. And this has been very exciting because each new one that we can get of this rare type is valuable. And then I got an email from a guy in Sweden, Roger Persson, and he did not do any observations himself, but he had the clever idea to compare the first Palomar sky survey from the 1950s with the second Palomar sky survey from the 80s. And of course, he cannot sit and sift through these visually. So he took the scans that you can download and wrote a computer program and compared every single star in both, and he found one that was not in the previous. And again, I took spectra and confirmed that it's a beautiful FU Ori object. So these are really, really valuable contributions that amateurs have made to this type of study. And the FU Orionis objects, as they have these disks, they crash onto the central star, then the heat and the release of energy from the disk drives big outflows. And so there are very substantial winds that leave the star at several hundred kilometers per second. And this is another feature, special feature of these stars. Now, there are a group of stars, young stars, that, as Michael, he said, they erupt about 5-6 magnitudes, but they only last for about a year. And they have very different spectra from the viewers. And one of the things that people are really trying to study at the moment is how does this whole zoo of erupting objects relate to each other? And this is something we don't know. And it is something that we try to, every time we find an erupting star, and we find more and more now that we have all sky surveys, then detailed studies of each, and eventually we hope to have enough material to make a coherent picture of why these stars, they undergo and these eruptions, and how they relate to each other. And I mentioned the all sky surveys, and of course the most massive of all survey telescopes will be starting in about a year. The Large Synoptic Survey Telescope, or as it's now called, the Vera Rubin Telescope in Chile. And I visited the construction site recently, and it's an incredibly impressive facility. And it will survey the sky with about 200,000 images every year, and will create an amount of data that's so large that no human will ever be able to look through it. So half of the construction cost of this telescope has gone into preparing software that can sift through these millions of events that will be released, and find the needle in the haystack that's interesting. And the hope is that we will be able to find many more FU Orionis objects thanks to this and to other surveys. And I'll just finish off by saying that if any of you are interested in knowing how the study of the Tauri stars began and what we know today, I have written a book about the father of early stellar evolution, namely George Herbig, a former colleague of mine who died a few years ago at the age of 93. And he almost single-handedly formed the basis for all the studies we do today in star formation. And on this URL that you have underneath here, you can download the book for free. And the SP1 means Special Publication 1. So with that, thanks for your attention, and I will pass you on to Bill. Let me stop sharing. Right.
Great.
So
Do we want to have any questions for Bo, or should I just go right on now and then we'll have questions at the end? Is that the way we're going to do it?
We'll have questions at the end.
Questions at the end. Okay. Bo just gave us a beautiful description of stars that erupt, that appear. Young stars do everything, as you've heard from Mike. And so I'll talk about stars that go down and disappear. And I'll talk, I apologize for talking about one in particular because it happens to be, have become the only star in my universe. So this is an example, and I'll take this as an example of stars that, young stars that do the opposite, that kind of disappear sometimes. And I think, you know, before I get into the details of this is one of the great things about having amateurs and, you know, professional astronomers always say we just are so thankful that we're in a profession where there are so many dedicated people like yourselves and have been over the years who make such tremendous discoveries and contributions to our field. You know, astronomy is the thing I heard. Can you imagine like a society of amateur dentists? Amateur dentists don't make contributions to the profession, I don't think. We're so fortunate to be in a field, amateur astronomy, where the universe is so vast. And sometimes people think, oh my gosh, we've been studying it so much and there's all these professionals. And well, there are very few professionals, really. There's only like 10,000 professional astronomers in the whole world. And, you know, only a minor fraction of them are working on young stellar objects. And even though we have machines and surveys and all this stuff, we're still limited by people. There, you know, whether a star is discovered on a machine or a photograph or something to have disappeared doesn't matter. It's, does somebody notice it? Does somebody then investigate why? Does somebody take a lesson from that? Does somebody advance our knowledge? And that's all people driven. And we're so, because there are so few professional astronomers out there, we're so happy to have vast numbers, really large numbers of people who are willing to go out there on their own and help out. And the universe is so vast and there's so much going on that we are nowhere near having too many people. So thank you all to the audience for your great contributions. And the AAVSO has been probably at the leading edge of this for decades. So here's a star that disappeared. We discovered this one in 1995. So it's 20 years old now, 25 years old. And it was called the winking star because it disappeared. Here you can see it one night. This is taken with a 24-inch telescope. So at a lousy site, I mean, I don't mean lousy, it was in Connecticut. I mean, it wasn't on a mountaintop in Hawaii or something. It was just in a, you know, parking lot on a campus in Connecticut, 24-inch telescope. And we were monitoring young stellar objects and young regions. And one night, this was brought to me by a graduate student who was looking at the images. And we noticed that there was a star that basically disappeared. It didn't disappear entirely, but it went below our ability to see it. And we didn't know at the time that this was actually a known variable star, V582 Mon. We just started calling it KH15D after the numbering system that we used for numbering our variable stars. So this was at the 24-inch telescope in Connecticut. So here's the neighborhood of KH15D, and this will be familiar to many of you. This is the Cone Nebula, so this is part of NGC 2264, a nearby cluster. And KH15D is a little star up there. It's about a 14th magnitude star normally. It sits pretty close to a 9th magnitude star, so that makes it a little bit of a difficult object. And whereas some of the more advanced amateur astronomers have and continue to observe this and produce data for us, I don't recommend it to anyone who is faint of heart. It's not a good starting place. The kinds of projects that Bo was talking about and Mike has talked about, where people monitor known young stellar objects and look for very big changes, either the star all of a sudden appeared somewhere or a star all of a sudden disappeared somewhere. Those are much better projects, especially for getting going. But if you're a really good photometrist and you know how to handle scattered light and calibrations and all that stuff, this is a star that we could definitely continue to use monitoring for. And back in the early days, many amateurs did contribute to this, organized by Katrina Hamilton, my graduate student. We had something like our first paper on this had about 25 authors, more than half of which were probably amateur astronomers. So it has an important contribution from amateurs. So what's interesting then is not just to find this, but then to figure out what's going on. Why would a star wink at you? Why would it go away? And this is 25 years later. And we have observed this thing, I think, with every telescope out there. It wasn't our goal just to observe with everything out there. Our goal was to figure out what's going on. And it turns out that young stellar objects are interesting because they radiate at a whole variety of different wavelengths. And so you need different things. You need Spitzer for the infrared and Hubble and so forth. And you even use radio telescopes. So young stellar objects are exciting because they cover, you know, they radiate at a range of things. And these are just some of the people after 25 years of looking at this, some of the people who have been on our teams and gotten involved with it. And we're from all over the world, all the way from Uzbekistan to Heidelberg. I'm sure we have somebody from Hawaii here, and many students who have gone on to careers and so forth. So this has been exciting, not just for the science, but also it's been a kind of a project that has involved a lot of people. And just because I could, this shows you kind of the history of the excitement of it. There was a big bump of papers. This is papers at the beginning, and then there was a steady stream. And recently we're beginning to get another increase in citations and reads, because the star, even after 25 years, continues to be interesting, continues to be surprising. Josh Wynn, who got interested in this as a graduate student, calls it the gift that keeps on giving. So it continues to surprise us. So here's a heck of a light curve for it. This is a star which, and I'm sorry I didn't have the information before 1995. So this is from our beginning of our work on. This is its light curve, and you can see it continues. It winks on at a magnitude up near 14th magnitude down to like 17th magnitude. And then for a while it was winking down to 18th magnitude or 19th magnitude. And here you get up to 2010, the star itself almost disappeared down to about 17th magnitude, but was still varying down to 19th. And then to our great surprise, our prediction, the predictions of all the theories and so forth, was that this decline was just gonna go like that. And as I tell my students, this was supposed to coincide with my retirement at around 2010 or 2011. But darn it, the star did something we didn't expect, and it reappeared. And now it's getting brighter and brighter and brighter and brighter, and it's come back, and it's still doing its winking, and so away we go. I wish I had put the data from before here. We have data that goes all the way back to 1950 or so from archival stuff, and the star didn't start its winking behavior until around, we estimate, 1990. Nobody was really looking much back then. But prior to that time, it was a variable star, but it was brighter than 14th magnitude, and it was just kind of an ordinary T-Tauri star. It showed some variations, but it didn't show anything like this kind of winking behavior. So this is another key point about young stellar objects that Mike made and that Bo made. They changed their character. Just because you think you know the star, T-Tauri, for example, doesn't mean that tomorrow it's not going to do something new and different. You know, the beautiful example of McNeil's Nebula that Bo talked about. Who knew that a star was going to just turn on at that time? I don't know if there's any other class of stars out there that just has that surprise behavior. And that is, by itself, is one of the really nice reasons for continuing to watch them. Because you might have watched it and watched it and watched it, and it didn't do anything interesting, and then all of a sudden it does that. And that's the way young stellar objects are. So what's the explanation? All the observation, all the people working on it and everything. So what we've finally come to understand about this star is, and this is true of probably a lot of the objects that go through these dippings and disappears, they get covered by something. Something around them covers them. So at first you think that it might be something orbiting it because then this is what we thought here. Oh, maybe there's some big new forming planet or something that's in a disk around it. It's going to cover it and make it wink on and wink off like that. But the answer turned out to be more complicated and interesting. And part of the answer was that this star, like many stars, like about half or more of the stars, isn't a single star, it's a binary system. And a lot of the effects that we see out there, Bo was mentioning this in terms of FU Orionis eruptions, is triggered by binaries. And binaries are not rare, binaries are common. They're as common as single stars. And so this turned out to be a binary system, and it's shown over here, A star and B star. They're about the same mass, they're about 7/10 of a solar mass. So they're in an orbit, and the orbit is pretty much inclined to our, pretty much edge on to our line of sight. We tipped it a little more in this representation just so you could see the stars, but it's pretty much there. And then what has happened is that beginning around 1990, and this is around 1995 here, it's been occulted. The system is being covered by something sliding in front of it, as kind of depicted there. And so star A, which previously you would see A all the time, if this thing wasn't there, the occulting part wouldn't be covering A. Star A is now dipping behind and coming up, and every time it comes up, we can see it, and every time it dips behind, we can't see it, so it winks off, and so forth. It doesn't wink off completely because there is some reflection here, and then star B was there, and star B in its orbit, when the way it goes, when this star gets to perihelion, this star gets to perihelion. So at a given edge, you can actually have times when star B is appearing in the middle of when star A was being eclipsed, and that's what's sort of shown here. And here, we would be seeing star B peeking out at perihelion, whereas here we would see star A. So as time went on, this thing marched across, and that's what caused it to change and gradually decline. And by the time we got up into the 2000s, this thing here was covering the whole system, and that's when we thought it was going to go out. The reason nobody could predict when it was going to come back on again is because we knew nothing about this edge. of the whatever it was that was sliding across the system. We knew where this edge was, the leading edge, but as far as we knew in all the models, this went on to infinity. You know, it was very large, so we expected this to go out. Well, for some reason, and nobody, as far as we know, it's a cosmic accident. It turns out that the size of this screen is about equal to the size of the orbit projected on the sky. And so the total covering only, the total covering only happened in 2010 and 2011. And by 2012, whoa, what was happening? Look at that, the other star was beginning to peak out. And my graduate student at the time, Holly Capello, who's now a professional astronomer, I remember her walking into my office one day and going, "It's back." Yep, the star was back again. And so now we had to reinvigorate it. I had to put my retirement plans on hold. And now we're following this thing as star B gradually emerges. And now we're getting to the point, the exciting point, where star A is beginning to emerge again. Our old friend star A appearing, because this edge has now moved far enough here that star A is beginning to. So what an incredible thing. Who would imagine? You know, this is kind of the physical system. Here's the binary system, and there is obviously a ring of material which is inclined. This shows you highly inclined. It probably isn't inclined that much, but inclined to the orbit of the binary. And so what's happening is precession of this ring is allowing us to look at the system from different configurations. And so we're actually seeing a precession on a time scale of like 100 years. That is, so we have a system that's kind of like this. This is the famous HL Tau system. But I show this only to tell you that we can tell from the precession time scale that that ring that we're looking at in KH15D is way close in. It has a diameter, it's at about 3 astronomical units. So it's way close in, closer in than we can probe these rings around young stars, and their disks are now known to be quite common. But we don't have one that, even with the ALMA resolution, that really probes quite as far in there. So 3 astronomical units is really an interesting place. And time, we can date these stars by putting them on an HR diagram, seeing how old they are, and they are around 2 to 3 million years old, and they have a total mass of about 1.3 solar masses. So this isn't too far from a solar system-like thing at an age of around 2 to 3 million years. It's a binary, whereas the solar system is a single star, but the binary is so tight, the binary stars have a 48-day period. They're very close together. So in terms of the ring and what's going on at 3 astronomical units, it's not that much different than what happened probably in our solar system billions of years ago. So what we're trying to do and have been trying to do is exploit a beautiful thing that nature gave us, a odd system discovered by serendipity. We didn't set out to look for this thing. We just discovered it when we were just monitoring young stellar objects. And it's the kind of thing that you can discover. I threw this picture in for Bo. This is to show you that our system does have a tiny little outflow here. It does have like a set of sort of analogous to Herbigaro objects, like an outflow. The outflow is seen both in shocked H2, hydrogen, molecular hydrogen, and also in CO. This is a carbon monoxide outflow gas, and they line up extremely well. And there is this incredibly puzzling little, here's one of those little puzzles of life. Why the knots here all line up beautifully, but why is the star not right in the center there? It's offset by that tiniest little amount, but it's a real amount. And so we don't know why that is. This thing is certainly associated with the system. It even has a little hook of gas that brings it right in there of emission. But why that is not sitting right there, we don't know. The mystery. And then I mentioned that now we're having the fun of comparing the trailing edge to the leading edge of this ring. And the leading edge was amazingly sharp. This is the kind of light, how the light disappeared when this leading edge, when a star came across this leading edge, it was like a knife edge. It was really sharp. Whereas the trailing edge, much fuzzier. The trailing edge is fuzzier, and it's also clumpier. We're seeing events where, oh, instead of being up here as the star comes out, it's all of a sudden down here. It's encountering a denser clump of material in this trailing edge. So by seeing the light through those clumps, we can use the background light as a probe of what's in the clumps. And we can study planet formation, asteroid formation, who knows what's going on inside of that ring as a result of that. And this harkens back to a picture that Mike showed about the wavelength dependence of the radiation. So the clump is bigger in V and smaller in R and smaller in I and smaller in J and smaller in H. And as you go to the infrared, the light is more penetrative of the clump. And so the clump doesn't really affect the infrared radiation as much as it affects the visible radiation. So this can tell us information about the nature of the dust in the clumps. And we can also get spectra. And what we find is that the spectra show lines of ice and methane. So we see water ice and we see methane ice. So this thing seems to be sort of at the edge of the ice line. And surprising to us, we were expecting to see silicates, but we actually saw ices. We were seeing clumps of ice. So there is still an incredible amount to learn. I listed 8 little things that we might be interested in learning here. But we need to stop. We need to keep watching this thing. One of the sad things is that our major monitoring telescope, SMARTS, it was an operation that happened at Sartololo Observatory, is now offline. So the contributions from amateur astronomers, only, again, this particular project is not for the faint of heart, and contributions from other telescopes around the world have become much more important as we keep an eye on this thing. So that's just one example of the kinds of objects you can find, discover, have fun watching out there among the young stellar objects. So I'll stop there.
Thanks, Bill. Okay, we can now open it up to questions. So what I'm going to do is just pick out the questions as I go and deliver them to the person who I think can answer them the best. If I don't know what that might be, then I will just throw it out there and have you guys answer as you feel like. So this first question, I believe, was specifically directed towards Mike. It says, in the first photo you showed, it seemed as though there was a horseshoe of empty space centered on the nebula with very few stars. They were asking if that is just a coincidence or if there is dust there.
Oh, there's undoubtedly dust there, yeah. But again, please, please, I'm open to correction. But I should think it's almost certain. Yeah, because these are very dusty environments.
So the next question is, I believe for Bo, and it says, can you speak more about the physical processes that drive polar outflows?
Yeah. what happens is that when material from a circumstellar disk crashes onto the star, the problem that is in getting material from a circumstellar disk which has angular momentum is that angular momentum is conserved. So the only way that you can get some material to fall down on the star is if some other material is ejected. And so that is, in some of these very complex magnetic structure models, that is a certain point where you can divide material that will fall into the star and material that will be ejected. And what is ejected will follow magnetic field lines that slowly rise upwards perpendicular to the disk. And it's along those magnetic field lines that you see the Herbig-Haro jets. This happens on a scale that is very, very small and much, much smaller than anything that we can resolve with current techniques, even with ALMA. But we can see the large scale effect of these outflows because they occur supersonically, and therefore they cause jets, they cause shocks that show up as Herbig-Haro jets. And in some cases, for very young stars, these Herbig-Haro jets, they are beautifully collimated.
Cool. So the next question, I honestly don't know if it has a specific target, but it says, some years ago, the BAA VSS looked for correlation between the variations of RR tau and its associated variable nebula. Our results were inconclusive, mainly due to the difficulty in obtaining photometry of the Fate nebula. They're wondering if anyone has looked, if any further work has been done in this particular field, or on this particular field, I guess would be a better question. Does anybody happen to know?
I do know that the sort of RR2I area is a heavy emitter of X-rays, so there's obviously something, you know, there's something very dynamic going on there. Yeah, I think there is a little associated nebula, but I don't really know much more than that.
Well, I can add that one would expect to be able to follow changes in the brightness of a star in the way it illuminates the surroundings. And it has to be very clear cut. So FU Orionis objects, they're particularly good for that. The FU V1057 Cygni, when that brightened, a series of photographs showed the light echo moving through the surrounding clouds. So that's the kind of relation that one can see.
Cool. So the next question is for Bill. It says, in Dr. Herp's slides showing the linear feature where CO emission lines up with the shock H2 emission, it looks like there are several other linear features in that slide that are parallel to the main feature, as if they were banding in the image. What causes that?
Yeah, those are just artifacts of the image reduction. They're not real. It's a radio thing, and yeah, those are not real. The only real feature is the actual CO that's associated with the optical image.
And the next question, I don't know exactly what they're asking, but they are curious about limitations of support or participation in Bortle 8-9 skies. If there are specific techniques, or is this a lost cause? I'm afraid I don't really understand what Bortle 8-9 skies means. So if nobody else does, then I will ask Jack to clarify his question. And I will move on to another one. So it's REV 582 Mon. What photometry observing cadence is recommended? Rapid time series, 1 measurement per night, once a week, etc.
That's a great question, and it's something you as a variable star observer, you always need to think about, what are the time scales on which the variability is occurring. So in general, in our field, we're not dealing with, white dwarf stars or highly condensed objects or nova and so forth, where the variations happen on very short time scales. So generally speaking, and there might be exceptions, but generally speaking, we're dealing with things that happen on time scales more like hours to days, as opposed to seconds to minutes. There are, you can get some cases, but for generally speaking, an observation per night or an observation per hour is probably going to be overkill. For our particular object, KH15D, for example, 1 observation per night is fine. It doesn't really do anything interesting on time scales shorter than that. So the cadence in our case would be one observation per night. Bo might have some examples where it would be more interesting or valuable to have shorter time frame observations, but I think that's kind of a guideline for YSO.
Well, I will second what Bill he said, and especially different physical mechanisms, they operate on different time scales. And for example, the flares that Michael was talking about, they occur on very short time scales of half an hour or so, from eruption to they have died out. And then there are very long time scale changes like the one on KH15D. And there may be things in between that we don't know about. And so my colleague Josh Wallowend and we have had for years a key program on the VISUS telescope where we are monitoring whenever the Orion Nebula cluster is over Air Mars 2. We just sit on it, and every 2 minutes we take a new image. And so we have tens of thousands of images where we hope that we will be able to get a complete picture of all the different types of variability that you see in young stars from the minute time scale and up to the several year time scale.
Cool. So I got some clarification on Jack's question. Essentially, he's asking if there are techniques for doing astronomy in places where there's a lot of light pollution or bad skies, or if it's just a lost cause. I can give a little bit of information here. Essentially, it all kind of depends on what you're looking for. So there is still a lot of stuff that you can do with brighter stars, and there are brighter stars that are seen in pretty much anywhere. So most of the Orion stars, for instance, are bright enough that you can see even in Boston, for instance. So you may have to change the star targets that you look at. As far as dealing with light pollution or techniques, I don't particularly know of any. That's not to say that there aren't any. So if anybody else has any ideas, feel free to jump in. Basically, if you live in a more light polluted area, you're limited in the number of targets that you can look at, but that doesn't mean that there aren't still interesting targets. Maybe not a ton of YSOs in particular, but lots of massive stars, which are kind of YSOs, and other objects as well that you still can see.
Yeah, I'll just jump in there. I would highly recommend CQ Tauri, which is very, very active. varies roughly between magnitudes 9 and 11. So, you know, probably easily visible from a light-mounted sky. Obviously, it depends what the size of your instrument is. And of course, you've got FU Orionis, which is even visible in binoculars. You don't even need a telescope. If you use a small telescope on that, then you'll be able to see FU Orionis at the same time. So then, you know, there's 3 stars to start off with, and they can all spring surprises, as we've seen.
I would like to add that one object that is very interesting is in the Orion trapezium. The individual stars in the Orion trapezium is around 6 magnitude or so. And 2 of them are eclipsing binaries. One has a fairly short period, but one of them has a period of the order of 2 months, or a little more than 2 months, and has an eclipse that lasts more than 24 hours. It's a 1 magnitude eclipse. And because of the length of the eclipse, we actually have those eclipses covered very poorly. And it would be very interesting if the AAVSO would start a campaign and collect data from around the world so that one could assemble these eclipses. And the period is very well known, so you can ahead of time say which are the 24 hours in which this star fades. And just from a purely aesthetic point of view, it's actually really fun to see that the trapezium changes appearance, and you can see it with your naked eye when you look into an eyepiece.
If I could just add on to that, besides the 4 trapezium stars, there's a star which BM Orionis, which is, I think it's not one of the 4 trapezium, but it's one of the next, it's right in there in the trapezium region. And that has a period, it's an eclipsing binary, with a period of around 6.0 days or something like that. It's very close to 6-day period. And so because of the cycles of it, it's very hard to get the eclipse of that, get many observations of that eclipse. And so, and it's a changing eclipse, which has variations in, you know, how wide it is. And so it's not an eclipse by a star, it's an eclipse by something more than a star. And so the trapezium stars are probably extremely young. Some people, you know, dynamically that system can't last for very long, you know, measured on the time scales of tens of thousands of years, the dynamical interactions are going to break that system apart. So it's an extremely young system. These are more massive stars than we typically observe as a young stellar object thing. But it's, as Bo was saying, it's just fascinating that something as well known as the trapezium still has all these cosmic mysteries associated with it that can be addressed by careful observation, including amateurs.
Yeah, PM Ori is in fact one of the trapezium members, and he was the one that I was alluding to.
Oh, PM Ori is what you're talking about.
Yes.
Yeah,
And,
I couldn't remember it. Yeah.
What Bill says is really true. One of the problems that professional astronomers have with trapezium is that if you try to point a several meter large telescope towards the trapezium, you're going to be in trouble. And so this is something that by definition you need a small telescope to be able to handle.
Yeah.
Because there are challenges because of the proximity of the stars, but it can be overcome.
Okay, so I will try to, do you guys mind sending these objects you listed by email so that way we can compile a list and we'll put it online or something for people to be able to browse through for interesting targets? And I will move on to another question. So it says, in the last year or so, I've started trying to find which YSOs reveal a nebula, Herbig-Haro, in visual observations. So I enjoyed Bo's book. Oh, so this is just a comment, not an actual question. But it says, I just saw the Parsemyan 21, and it's an FU Ori star. Cool. Let's see. So this is a question, I believe, for Bo in particular. It says, in the slide showing the near IR spectra of a number of FU ores, what molecule gives rise to the band with lines at wavelengths of 2.3 microns and longer?
Oh, okay. These are the CO bands.
Okay, cool. So then they said, what writer YSO would be of interest for low resolution spectroscopic monitoring? And they specifically clarified that they mean FU Ori type.
Well, the problem with FUORs is that their spectra hardly ever change. I mean, the changes that we've seen in FUOR spectra over decades are imperceptible. So monitoring is not really interesting. What is interesting is to get an early spectrum. And of course, the holy grail in variable star, young star in that field is to catch a few on the rising branch, because we are very, very interested in finding out how does a Tauri star transform into a FU Orionis object. We don't know.
Okay, sorry, I was just looking through. So I'll mention to everybody all of the links that were discussed, or specifically the Herbig link. If you guys have any other ones that you want me to email out, I will be in your post-webinar email, so don't worry about that. I am assuming that Mike intends to post his slides online. As for the other guys, if you are willing, we can post these online as well.
Sure.
And yeah, I think that looks to be all of the specific questions. So unless the panelists have anything else, I think we can conclude there. Thank you so much for attending. I want to do another shout out to our sponsors again, Voice Astro and ATIC Cameras. Next week will be the solar section, so please stay tuned for that. And thank you all again. Have a great rest of your day, night, morning, whatever.
Bye now.
Bye now.